Okay, so we're going to be looking a bit at partial fractions in this session. Um, just to clarify, the title of the topic is partial fractions, but you're not actually going to be learning how to do partial fractions. In theory, you know how to do those already. This is the topic of partial fractions under the umbrella of integration. So we're going to be using partial fractions in order to integrate functions that we otherwise could not integrate. However, it might have been a while since you've used partial fractions, so just to remind you or get you back in the groove of doing partial fractions, have a go at doing this one here. I wouldn't say it's a particularly difficult one, but you do want to make sure you can do it. So give it a go. This one first. Can you express this in terms of two partial fractions? And pause the video now. Okay, so let's give it a go. So hopefully you remembered that to express something in partial fractions, you first need to write its partial fraction form. This is a simple case. We're not going to go through all the various possible cases at this stage, but you do need to be aware of them. You know, a plus b, or perhaps sometimes it'd be a and then a bx on the top. It all depends on what you're trying to do. But this is a simple case, two linear terms on the bottom, and they're both different. So it can be written in this form. And then we'll just do the usual, multiplying both sides by this x plus 1, x plus 2, we end up with the following. And then hopefully you remember that you've got two methods. One is substitute values for x, and the other is try equating coefficients. Usually the substitution one can be a bit faster in most cases, so let's do that. When x is minus 2, what information do we get? Notice I just added an extra line here because technically these are identities. It should work for any value of x. So we'll get minus 6 plus 4 is minus 2, and in this case it's equal to 0 lots of a plus minus 1 lots of b. So that tells me that minus 2 equals minus b. B is therefore equal to 2. If I then substitute minus 1 in to cancel the second term, I'll get minus 3 plus 4 is 1, minus a plus 0 lots of b. In other words, oh, is it minus a? No, sorry, that would be 1a, wouldn't it? So we get a plus 0b implies a equals 1, and that's it, we've done it. Replace a with 1 and replace b with 2, and we've expressed it in terms of partial fractions. Cool. Right, so let's start looking at how we can make use of this for integration. So my idea is to mainly teach this by example, so I'll give you a couple of examples of using it, but just before we jump into the example, let's just lay out roughly what we'll do each time. So the first step is we're going to convert an algebraic fraction into partial fractions, right? So this method of integration by partial fractions, you're going to be using it whenever you've got an algebraic fraction. I shouldn't say whenever, in some cases when you've got an algebraic fraction. So your first step is going to be to just convert it into partial fractions, okay, before you even do any integration. Then the second step is going to be that you'll apply the integral operator separately, right, or individually to each of those fractions. So you started with a single big fraction and now you've split it into multiple simpler fractions, and you're going to apply the integral operator to each of those individually. And then finally, just perform the integration. And quite often will be the case, because we're now working with fractions, I'm going to say here probably, but it's not always the case, probably you'll use a form of reverse chain rule. And that can be of various types. It can be of the type where the derivative of the bottom is the same as the top, or it could be of the type where you've got a derivative multiplied by a function to some power, right? So that's the f dash x times f of x to the n kind of form. But let's take a look at some examples now. That's the general idea. It's not too complicated, I hope. Let's take a look at some examples. Okay, so we've got 3 examples to work through. I'll do them one by one and then just clear the space each time, because we've got a bit of working for each. Following this example, you've got questions to try yourself, but feel free to watch for these 3 examples, see how we do. So the first step is going to be to get our partial fractions right. So you can follow along with me, or perhaps skip ahead slightly if you're absolutely sure you know how to do it. But or you can try and race me to the answer. Let's see how we do. This particular partial fraction I should be able to express in this form, which implies the following. And then I'm going to substitute. X as 2, gives me the following for b, and I'm going to substitute x as 1, which gives me the following. Sorry, this should be a +1 here, shouldn't it? So x is -1. Let's take that back. Gives me -6 equals -3a, implies a equals 2. And here I should have put a 3b, shouldn't I? Yeah, because x was 2. Okay, that implies b equals -1. Okay, so we've got it. This is the same as 2 all over x plus 1. And then change that to -1 all over x minus 2. Just double check that. Yeah, so let's remove some working. So that's the first step. We've turned it into partial fractions. And then the second step was we're going to apply the integral operator separately to each of these fractions, right? So on the left hand side, I'm trying to find this integral, which is this, but that I can convert into 2 individual integrals, and in this case I'm just going to leave the minus sign in between them. So we now work them out separately. The integral of 2x plus 1 and the integral of 1 all over x minus 2 with a minus in front. So in the first case, we're going to use the derivative of the bottom equals the top rule, as I call it. The derivative of the bottom, x plus 1, is just 1, but I've got a 2 on the top, so we're going to halve, and I get this. Plus c, I suppose. And for here, the derivative of the bottom is 1, which is the same as the top straight away, so we get ln of x minus 2, but with a minus. And again, I suppose we can put plus c. So that gives us a final answer of the... Oh, hang on. Oh, sorry, this shouldn't be a half. This should be 2. Sorry, I've rushed it. Yeah, because the derivative of the bottom is 1. So we've got this, and then we're going to stick it together as one final form, like so. But this can be simplified. So in this case, here's how we're going to simplify it. We're going to use all of our log rules, right? So that 2 ln of x plus 1, let's bring the square up as a power. So we'll get ln of x plus 1 squared. I can get rid of the mod now because it's a square number. And then this minus ln x minus 2 tells me I can divide these two expressions. So I'll end up with x plus 1 squared divided by x minus 2. So this is just using log rules, nothing else. And that's it. That is our final answer. And we do still need the mod on the outside here because the x minus 2 component had the mod and we can't get rid of that. So that's it, we've done it. We've integrated quite a complicated looking function. Turns out to just be, well, I suppose another complicated looking function. But this is our method, and this is what we're going to refer to as integration by partial fractions. Let's have a go at part B and see how we do. So for part B, let's take a look at what our form's going to be. So for B, we've got, well, I suppose I'll quickly write it. And we've got a repeated root, not a root I suppose, but a repeated polynomial there, x minus 2 squared. So that means our form is going to have to be as follows: a all over 2x plus 1 plus b all over x minus 2 plus c all over x minus 2 squared. You might sometimes write these two the other way around. It doesn't particularly matter. B and c are interchangeable, at least until we find their value. So multiply through the denominator 2x plus 1 x minus 2 squared on both sides, and we get the following. Let me try not to rush this too much. Okay, and in this case, I don't want to labour the point too much. You should be able to find those values there. Substitute x equals 2 perhaps, substitute x equals minus a half, or alternatively equate some coefficients. You should be able to find the values of a, b, c in that case. In this particular instance, they're going to end up as follows: 2, 3 and minus 1. Okay, so skipped a bit of work there, which you should know how to do. If you don't know how to do it, then do make sure you give it a try yourself. Okay, so we've done our step 1, we've done the partial fraction component, and now we are going to start integrating things. So I want the integral of this, which is the integral of that, which is the integral of that, plus the integral of that. This first one over here, the derivative of 2x plus 1 is 2. That's exactly the same as the top, so that's very convenient. We get ln of 2x plus 1. Let's take a look at this one. We're going to get derivative of the bottom is 1. I've got 3 on the top, so it's going to be 3 on the outside, ln of the bottom. I should say x minus 2 there. And finally, we've got this one, which is a bit more tricky. Okay, so just to be clear, these arrows, this is, you know, the derivative, right? It's not the alternate form. This is the I shouldn't say derivative, integral. Okay, this is the integral in each case. Whereas that other one, I think we might have to do a bit of a rewrite before we can start integrating it. So to do that one, let's just have a little thing on the side here, and rewrite this expression minus 1 x minus 2 squared. That's just a power, really, isn't it? It's well, we've got a minus 1 on the outside, and then x minus 2 to the minus 2 dx. This we can then do with a chain rule, right? So we've got a function to a power being multiplied by the derivative of that function, right? The derivative of the function x minus 2 is just 1, so it's a constant. So this we can do by reverse chain rule. Add 1 to the power, differentiate, and see what we get. So let's try it. What's the derivative of x minus 2 to the minus 2? Let's forget about the minus 1 for a moment, because we're just trying it out. We get minus 2 times x minus 2 to the minus 1. Oh, sorry, I wanted to differentiate the minus 1 version, didn't I? So x minus 2 to the minus 1 differentiated gives me minus 1 times x minus 2 to the minus 2 multiplied by the derivative of x minus 2, which is 1, so it stays as it is. And in fact, we've got it first time. That's exactly it, isn't it? Minus x minus 2 to the minus 2 is this thing here. So we don't even have to tweak it. So that tells us the integral of this one is this, which is just 1 over x minus 2. So let's write that in. It's 1 over x minus 2. And all of those have been added up. So we've got a bunch of plus signs, a final plus c, and we're just about done. So that is actually the answer in some sense, but we can collect the log terms together. So by default, even if you're not asked to, you should be collecting together these log terms using log rules if you can. Whenever you've got the addition of two logs, it's considered simpler to have it as one log expression. So this 3, which I delete, is now going to be the power of this x minus 2. And those two logs, ln of 2x plus 1 and ln of x minus 2 cubed, we're going to multiply those two expressions together and create a single logarithm. So we get this. And we've still got 1 all over x minus 2 on the outside. We can't do much about that. And we've still got our plus c. And that's it. There we have it. That is our final answer for part B. So finally, let's do part C. Bit of a trick to that one. It looks like it's a single term on the bottom, right? 1 minus x squared for part C, but hopefully you can spot and immediately think to yourself 1 minus x squared. That looks like quite a standard form, and it's actually just difference of two squares. So what we should do is, and you're going to have to spot this in the wild yourself, convert that immediately into 1 minus x times 1 plus x. Okay, so difference of two squares, a squared minus b squared is a minus b times a plus b. Okay, and then we're going to split that into the partial fractions. In this case, you should be able to do that yourselves. I'll skip the working for now. You'll get an a of 1 on the top and another b of 1 on the top, these two constants here, when you do the partial fractions. Okay, so that won't be done without working. You won't be able to just jump from this to this. You do need to use your rules of partial fractions to determine that. So that's what we've got, and then we're going to integrate that. We'll get the following. Integral of 1 all over 1 plus x is just ln of the bottom, quite convenient. And for the second one here, the derivative of 1 minus x is minus 1, but I've got a 1 on the top, so I need to multiply by a minus number. So it's minus ln of the bottom. And then we can nicely combine that, plus c, we can nicely combine that by dividing the two expressions, because I'm finding the difference of two logs. There we go, and there it is. Quite a beautiful little result there. Integral of this fairly harmless looking function is as follows. Cool, so let's see if you can do some questions yourselves. So I've got 3 questions for you on 3 slides. 3 questions on 2 slides, 2 on the first, 1 on the second. In the first case, number 1, just see if you can integrate these more basic partial fractions. I think finding the partial fractions form themselves, you should treat it a bit like a speed run. See how quickly you can do it. They're not particularly complicated ones. Try and use your substitution method. Get a and b very quickly, and then perform the integration. Don't forget to combine logs at the end if you can. And then have a go at part 3. Have to think about it perhaps a little bit more. You're going to do some definite integration. see how you do on those two for now. Pause the video now. Okay, and then finally have a go of this one. See how you do. And try and find it in the express form that has been requested of you. So you do need to be familiar with your log rules. Give that a go. Pause the video now.